natural numbers. Remember those were the counting numbers. Okay. So those are kind of the smallest set of numbers that we can talk about. They're the first numbers that came around. Those were natural, we counted. After the natural numbers, after the natural numbers came whole numbers. Okay. And these are just like the natural numbers except we added 0. Okay. Both are infinite, but the whole numbers have one more number in them than the natural numbers because they have 0, and the natural numbers start at 1. After we talk about the whole numbers, we got into integers. Okay, the integers included all of the positive whole numbers and all the negatives. Okay, at this point, we've doubled our numbers because we took all those whole numbers and we added all of their opposites. The next thing we're talking about now is the rational numbers. And you'll notice that every natural number is also a whole number. And every whole number is also an integer. And then the rational numbers are going to end up doing the same thing. Okay. When we talk about rational numbers, these are all the integers, all of the fractions, and all terminating or repeating decimals. Okay, by terminating, that's decimals that end, so 0.2, done, or 0.37569, but it ends. Repeating are decimals that have a pattern that repeat. So it can be the same number over and over again, 0.3 forever, or it can be a pattern that repeats over and over and over again, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So these are rational. And this is where we're talking about now, and that's why we're going to be converting between fractions and decimals because they're both the same thing. All integers can also be written as a fraction. 2 is the same thing as 2 over 1. That's why the integers fit in here. Rational numbers, by definition, are fractions. Okay. After that, we get irrational numbers. Okay, you know how every family has that one uncle or cousin that doesn't quite fit in, you know what I'm talking about? Mm-hmm. They're in your family, but they're just not really there. That's what the irrational numbers are like. These groups all fit inside of each other nicely. Every natural number is also a whole number and an integer and a rational number. Now, it doesn't go backwards. Rational numbers aren't all integers, but as you move out the circle, every one of these is inside the other ones, so they all fit. And then you get these irrational numbers over here that don't fit in with the rest of the group. These are non-ending, non-repeating decimals. So these are decimals that go on forever with no pattern and no end, like pi. You guys have heard that about pi, that it never ends and it never repeats. So pi is irrational. Square roots that are not perfect squares are all irrational. So like the square root of 2, the square root of 3, the square root of 17. These are irrational. they'll just keep going on forever. And there's never any pattern, and mathematicians have spent their entire careers searching for the patterns in these numbers, and they're not there. It just doesn't happen. And altogether, all of these numbers are real. Now, real numbers is a fairly new concept, and by fairly new, I mean in the last like 400, 500 years. But math goes back 3,000, 4,000, 5,000 years. So in the lifespan of math, fairly new concept, and that came about when they discovered that in order to solve some problems, they had to be able to take the square root of negative numbers, which can't be done. Because if you multiply two negatives together, you get a positive. If you multiply two positives together, you get a positive. So a negative number can't have a square root because there's no two numbers that you multiply together to get a negative. So they made one up. It's called I for imaginary. It's an imaginary number, and I squared is -1. And so when that happened, they had to create this whole other number system based on imaginary numbers. So in order to solve some math problems, it had to be done. It had to be done. So there's this group over here called imaginary numbers, and then when those came about, these became real. So you have real numbers and you have imaginary numbers. We're dealing with real numbers. So these are all like real. You can have a half of something. You can have 10 of something. It's concrete, it's real. You can have negative something, you owe money. That's a negative, it exists. What you can't have is, we are in rational territory here, which means we're not going to have any crazy decimals that never end or never repeat. So the definition of rational numbers is the set of all numbers which can be expressed in the form of a over b, where a and b are integers and b is not 0. Every rational number can be expressed as a fraction. Every whole number can be a fraction. Every negative number can be a fraction. Every decimal can be a fraction. Every mixed number can be a fraction. Integers are easy. Just stick it over 1. It's a fraction. Decimals take a little bit more work, but it can be done. The number on top is the numerator. And the number on the bottom is the denominator. Okay? What this is saying is if you have some fraction and you multiply the top and the bottom by the same number, it doesn't change the value. So for example, if I have 2/3 and I multiply the top and the bottom by 2, I end up with 4 and 6. But 2/3 and 4/6 are the same, they have the same value. Okay. 4 being 2 times 2 and 6 being 3 times 2. This would be the C, the 2. You guys probably all know this. They're called equivalent fractions. And to reduce it to its lowest terms, we're going to divide the top and the bottom by the same number. In this case, if we were going from 4/6 to 2/3, we would divide both the 4 and the 6 by 2. Sometimes it's really easy to see, like 4/6. Oh yeah, those are both even, divided by 2. Sometimes you've got multiples of like 13 or something, or 17, and it's not so easy to see. And guess what? It helps. Factor trees. Yay. I like them. Okay. For example, 130 and 455. Okay. If you see the biggest number that goes into them, the greatest common factor, you just divide by that. But sometimes you don't see that. For example, I don't know what the greatest common factor off the top of my head of 130 and 455 is. However, I do recognize that they both divide by 5. And so, a lot of times, I just start breaking them down by what I see. And it might take me a few steps, but that's okay. So 130 divided by 5 is going to be 26, and that's going to be 91. And here's where I go, okay. Start thinking about 26, I know we'll divide by 2. That's going to be 2 times 13. Okay. 91, I know, does not divide by 2.
Can you divide by 13?
That's what I want to check next. Is it going to divide by 13? Well, I don't know. 13 goes to 91. Well, turn a 3 into a 1, I'm going to need to multiply it by 7, correct? Make it a 21? Does that make sense? What I just said. So I'm going to try 7. Perfect. 91. So I have a 13 common factor. So I'm going to divide both of these by 13.
Wouldn't that be the highest number to divide them by?
Yeah.
In the beginning?
No,
No?
no, because I would have had also this 5. So their actual greatest common factor would be the 13 times the 5, which would be 65.
Okay.
See, again, though, I wouldn't have necessarily seen that. Now, the other way you can do this is I can make the factor tree from the very beginning. Okay, that'll divide by 2. No, 65, sorry. And that'll divide by 5. And then I can say, okay, well, this will divide by 5. And those match, so then I would try the 13 like I just did. And then I'd say, okay, I can divide by this and this because those both match. But I don't have to actually do that division anymore. I cancel them out and keep what's left.
It's pretty much just the opposite of what we were doing.
Yeah, so here we were dividing to reduce, and here I did divide to reduce because I had to divide to get the factor tree, but once I have the matching things, I just cancel those out, and what's ever left ends up being the numerator and the denominator. So hypothetical number that I don't, let's like say I get to the ends of my branches, and I have a 2 and a 5 and a 13 and a 3 on this one. And then on the other one, I have a 5 and a 13 and a 7 like I did before. The 5 and the 13 will cancel out. I keep both of these. And then that one. Does that make sense?
So you keep the ones like
The ones that don't match. You keep the ones that don't match because that wouldn't cancel between the two fractions. Does that make sense?
And you just add them together.
We'll multiply them. Here, we'll do
I'll
number.
multiply.
I'll do you want me to do this? I think this one will be the best with the factor tree method, the larger one. But what I'll do is I'll do 2 with the repeated division, and then I'll do 2 with the factor trees. So those will divide by 4. Yeah. I was gonna pick the easy one and say 2, but 4 works. And will 3 and 20 divide by anything in common? Nope, so you're done. And 7 and 56 both divide by? Close. You on the other side of that. $34 and 98 both divide by? How about 2? If all else fails and they're both even, pick 2. Sometimes you have to divide by 2. Oh wait, I was gonna factor tree these. Never mind. They don't divide by 2. Forget that. Okay. They have a 2 in common. So I'm gonna cross that out.
Should that end?
I have this 17 that was from 34
Over 49?
over 49 on the 7 and the 7. And then for 180 and 252, okay, so there's 180. They have this 2 in common, and they have that 2 in common. 5 and 3 and 3 are left on this one, and 73 left on that one. So 180 will be reduced down to 5 times 3, which is 15, times 3, which is 45, over 73. So, however you want to do it. Now, this is a mixed number. You guys all need that. So you have an integer and you have a fraction. This represents 3 wholes. And so like if this was pizzas, you'd have 3 whole pizzas and 4/5 of another pizza. Yep, pretty much. Okay, an improper fraction is an upside down fraction essentially because the top is bigger than the bottom. 19 is bigger than 5. Now, you may not know looking at them is that these 2 things are exactly the same. Did you guys all know that already? Awesome. My shorthand for converting from improper or from mixed to improper. You move clockwise. You start here. You go 3 times or 5 times 3 plus 4. So what you get is 5 times 3 plus 4. So 15 plus 4 is 19. And your denominator stays the same. So just, in a circle, starting at the bottom, go times plus. Times plus. So 3 times 6 plus 2 gives me 18, 20 thirds. And again, in my personal opinion, useless has now been converted to useful. 7 times 3 plus 5, 21, 26 sevenths. 5 times 2 plus 2, 12/5. And 11 times 9 plus 4. Go the other way. So when you go from mixed to improper, you multiply then add. to go from improper to mixed, you divide and subtract. That's really what you do. So, this is the whole number part of the division, and that's the remainder. And then the denominator stays the same, which you guys probably also already knew. That's okay, because we'll go over it anyway. So 5 into 42. 5 goes into 48 times. See, there's the division. There's the subtraction. And so I get 8 and 2/5. Anybody need me to go over any more of those, or is everybody okay? Okay. How about this? Okay. To go from a fraction to a decimal, you divide the numerator by the denominator. So I'm going to do 5 divided by 8, which doesn't work, as you know. So you add the decimal and the 0, so 8 goes into 50 6 times. Add another 0. 8 goes into 20 2 times. Add another 0. And 8 goes into 45 times. Terminating decimal. They can end up long, but they will end or repeat if there's a fraction. You will not have a fraction that gives you a non-repeating decimal, non-terminating decimal. So 5/8 is the same thing as 0.625. And 7/11 is not just for Sharpies. Nope, I went backwards, sorry. I was thinking about Sharpies. Okay, 11 goes into 7 6 times. 11 goes into 40 3 times. 11 goes into 70 6 times. 66. 4. You guys see the pattern yet? Do you remember how to draw that? How to write that? Yeah, with the line above it. So it's going to be 0.63, and the line has to go above both the 6 and the 3. The line only goes over repeating decimals, so if you were to get a decimal 0.2 and then it went 5, 5, 5, 5 forever or something, when you wrote that, the line would only go over the 5. Because if you put it over both the 2 and the 5, that indicates 2, 5, 2, 5, 2, 5, 2, 5. Okay, so just be really careful of that, because I will mark it wrong. Decimals. If you look at decimal places and place value, okay, this is, the 1 is tenths, the 2 is hundredths, the 3 is thousandths, 10 thousandths, 100 thousandths, millionths, 10 millionths, etc., right? And so the denominator of the fraction, a decimal with 1 decimal place is a tenth. A decimal with 2 decimal places is a hundredth. 3 decimal places is a thousandth. The number of decimal places matches the number of zeros. Okay, so what you do is you count your decimal places. And then your denominator has that many zeros. Okay. You put the decimal without the decimal point in the numerator. You know how many zeros are in the denominator, so it's going to be a 10, 100, 1,000, 10,000, whatever. And then you reduce. Okay, so if I was going to reduce this decimal, which I'm not going to make you guys, I'm not going to go through it, but I have 1, 2, 3, 4, 5, 6, 7, 8 decimal places. So I have to have 1, 2, 3, 4, 5, 6, 7, 8 zeros. Okay, so this number of digits matches the number of zeros, and you put a 1 in front of it. Now this is for terminating decimals only. I'll show you how to do repeating decimals after we've done a couple of these. Okay, so anybody want to write that down? Okay, 1 decimal place, 1 0. Reduce if possible. This doesn't reduce. 2 decimal places, 2 zeros, also does not reduce. 3 decimal places, you do count that 0, but we don't list it. 3 decimal places, 3 zeros. These are both even, so this one will reduce. That'll go down to 24, and this will go down to 500. I just divide it by 2. Still even. 12 and 250. Again, divided by 2 because it's easy. Still even. 6 and 125. We'll divide by 3, we'll not divide by 3, so like that. My thing, rather than have you do that, it's very similar to the other one. You count the number of decimal places. Okay. This is the number of 9s in your denominator. Okay. We had 1 decimal place, 1 6 repeating. We got 1 9. So 6 over 9. So 1 decimal place, 1 9. I can reduce that to 2/3. Okay, so we have repeating decimals. Terminating decimals, you still count the decimal places and you have zeros with a 1 in front of them. Repeating decimals, you count the decimal places and you have 9s. So when I come over here, I have 0.27, 2 decimal places, 2 9s. I can reduce this, they both divide by 9, and I get 3 over 11. 3 decimal places, 3 9s. 1 plus 3 plus 5 adds up to 9. These will obviously divide by 9. So 9 goes into 13 lots with 4 left over, and 45 gives me 15. And then 9 goes into this, it will be 111. 3 repeating, 1 decimal place, 1 9. I reduce that and I get 1/3. 2 decimal places, 2 9s. Those both divide by 9. And then 1 decimal place, 1 9. So we have this, but basically, if you're multiplying fractions, two things. Rule number 1, and this is very important. You cannot multiply mixed numbers. Doesn't work. It's improper math. It doesn't give you the right answer. It doesn't give you anything even close to the right answer. You cannot multiply mixed numbers. You have to convert to improper first. Once you're there, you have two choices. You can multiply, then reduce, or you can reduce, if possible, and then multiply. And the multiplication is straight across. So if I have two fractions, no, I don't want to reduce yet. And I'm multiplying them, and multiply straight across. 15 over 20. That one I can't reduce. I made it non-reducible on purpose. I'm going to talk about these options. I'm going to show you the comparison between the two. This, though, really important. And I'm going to, does anybody want to see why it doesn't work? Like how I can prove to you that it's not accurate? Yeah? Give me a nice number.
4 and 2 seconds.
Give me another one.
7 and 3 fifths.
Okay. Now, if I were going to multiply those as mixed numbers, you would think multiply the fractions, multiply the whole number part, correct? And that's like the logical thing to do. So I get 28 and 6/35. That's if you multiply mixed numbers. But I can't multiply. So this is 28/37. Okay. And this is 35/38. Okay, and just to make this easier, I'm going to go ahead and reduce that. 8, 228/7, which is this is correct. Is it anything at all like that? Multiply mixed numbers, multiply improper fractions. You multiply the exact same numbers because 4 and 2 sevenths is the same thing as 37. 7 and 3 fifths is the same thing as 38 fifths. But 28 and 6/35 is nowhere even close to 32 and 4 sevenths. This is wrong. Never do that. Okay? It doesn't work. And like you could get into like models of it, and I could show you that really this is actually right and that's really very wrong, but no. Let's just take my word for it on this one. We're going to do this two ways. One, we're going to multiply, then reduce, and two, we're going to reduce and then multiply. I don't care which way you do. You can multiply then reduce if you like that better, or you can reduce and then multiply if you like that better. Okay, so negative 2/3 times negative 9/4. Okay, negative times a negative is a positive. 2 times 9 is 18. 3 times 4 is 12. 18 and 12 will both divide by 2. So that gives me 9/6, which will divide by 3. So I get 3 halves. reducing first. Wrong kind of fraction. You guys might remember that's constants. You guys might remember it's cross canceling. Yeah, sound familiar? Okay, I look here and here. I'll see if they have anything in common. Yeah, 3. 3 and 9 both divide by 3. This becomes a 1, and that becomes a 3. And then I look between these two. 2, this becomes a 1, this becomes a 2. And I multiply 1 times 3, 1 times 2. If you reduce first, you multiply smaller numbers. Usually when you reduce first, you don't have to reduce at the end unless maybe you missed something. Like you reduce by too small of a number, then you might have to reduce again at the end. But some people don't like that. So either one works perfectly fine. Okay, I am going to reduce this one second, and I'm going to reduce this one first. Okay, so 3 times 9 is 18, 3 times 20 is 60, and those will both divide by 6, which will give me 3 over 20. Okay. You're right, 10. Thank you. Good catch. In my head I wrote 3, and so I divided by 3. On this one, I'm going to cross cancel first. 15 and 35 both divide by 5. 4 and 38 both divide by 2. 19. Yeah, 19. So I get 6 and 33. Now, before I go looking to see if this reduces, I double check these and see if any of those will reduce, either this way, up and down, or diagonally, which they don't, so I know I can't reduce them. I know that the new common popular way to talk about dividing fractions is KCF, which is like KFC except not, and it's keep, change, flip. But see, to me, that's too confusing because it's too close to KFC, and then you go keep, flip, change. Doesn't. Copy, dot, flip. So if I'm dividing fractions, I copy, I dot, and I flip. Copy the first thing, change it to a dot, flip the second thing. Copy, dot, flip. Because dividing by a fraction is the same thing as multiplying by its reciprocal. And I can show you the math as to why you have to do that if you want me to. Nobody cares. If you decide you want me to show you later, let me know and I'll show you. But if you remember copy, dot, flip, that's how you divide fractions. Copy, dot, flip. Now, big thing. If you can't multiply mixed numbers, you also can't divide mixed numbers. See, I told you mixed numbers are not very useful. Okay, you have to make them improper. Once you've done the copy, the dot, and the flip, and then you just multiply. So, fractions, copy, dot, flip. If you want, at this point, you see if you can cross cancel, which this one doesn't. So you multiply a negative times a positive is a negative. Negative 33/35. Easy enough? Okay. Copy, dot, flip. This one will pre-reduce if you want to. 3 goes into 3 once, and it goes into 81 27 times. And 2 goes into 2 once and into 20 10 times. 1 times 27 is 27, and 1 times 10 is 10. And then copy, dot, flip. 19 goes into 38 twice, but if you didn't see that, you could just multiply it out and then reduce it. Five eighths. Not that any of you guys would ever do this, because I know that none of you would ever do this, but I cannot tell you how many times I've seen people subtract fractions, and they subtract the numerator, or or add the numerator, and then they add or subtract the denominators. That doesn't work. And the reason you have to have like the same denominator is because think of pizza. If you have 3 slices of pizza over here and you have 7 slices of pizza over there, they had to have been cut into the same size. Then you add this together and you have 10 slices of pizza. Well, depending on how many, if it was like pizza that had been cut into 12s, you'd have 10 12s. So it would have been 3 12ths and 7 12ths. But if it was like 8s, then 3 8s and 7 8s, and you'd now have 10 8s. Does that make sense? So the denominator doesn't change because the denominator is just the size of the pieces, and the numerators tell you how many of those pieces you have. So you add or subtract the numerator, but you keep the denominator the same. So if I have there's an 8/3, and have 10/3. Think of a third as a thing, like some little plastic or metal block that says third on it. And you have 3 of them in this hand, and you have 8 of them in this hand. So you put them together, you have 10 of them. Okay. So these all match. 3 and 2 is 5. They're still 7ths. Nothing changed about that. 11 minus 5 is 6. That will reduce. Now, first of all, he's happy, so he's going to be a plus sign. So I can do -5 1/4 plus 2 3/4, which is actually going to be a subtraction. Or I can do -21 fourths plus 11 fourths. improper fractions are actually easier to add and subtract than mixed numbers because there's no borrowing involved. I just say negative 21 and 11 is going to be negative 10, and then that reduces. With this one, I'm going to have to subtract because I'm a negative and a positive. So I'm really going to do 5 and 1/4 minus 2 and 3/4, and 1/4 minus 3/4 doesn't work. So I'm going to have to borrow from the 5 and make that a 4, and I'm going to borrow 4/4, so I'm going to have to turn this into a 5. 5/4 minus 3/4 is 2/4. And then 4 minus 2 is 2, and this was negative, so negative 2 and 2/4. I borrowed 4/4. So I borrowed a whole, so there are 4/4. Yeah, that works, since this will reduce to that when you calculate. So this requires a little bit more work actually with the, you know, if you have to subtract because you have to do the borrowing, and then you have to remember you have to borrow whatever the denominator is. My recommendation, because this right here actually leaves a lot of room for mistakes, if you make them improper, all you have to do is look at the numerators, because the denominator is going to stay the same, and then that's just negative 21 plus 11, which you're more familiar with rather than borrowing fractions. So there's less room for error there. Does that make sense? Mixed numbers are this is one of those concepts that can be kind of complex. Rational numbers are all the fractions and the decimals, right? And all the fractions and the decimals occur between whole numbers. So if I'm on a number line, and here's 0, and here's 1, here's 1/2, here's 1/4, here's 3/4. I can find a number halfway between there, halfway between 1/2 and 3/4. This is 4/8, this is 6/8, this would be 5/8. And I can find another number halfway between there. And I can find a number halfway between there, and halfway between there, and halfway between there, and half and half and half and half and half. It can keep getting smaller and smaller and smaller and smaller. The space between 0 and 1 is filled with an infinite number of numbers. Because they get infinitesimally tiny. And I have a good way to represent that. So if you guys just hold on a second. Let me pause this.
It's like